Hey guys, thanks for clicking on part two of the FPGA or the IIR filter within an FPGA. I'm going to build on the design that I showed last time, and I'm going to show you how I implemented the AXI-Stream signaling within the Biquad so they can be connected up to the AXI-Stream interface, maybe like a FIFO or another Biquad to make a higher order filter. I'm going to start in MATLAB. I'll link the GitHub repository to all the code in this. This first block right here, similar to the last video, this is generating that test stimulus file. So I'm going to generate 250 samples coming from 16-bit unipolar positive ADC with a sampling frequency of 10 megahertz. So same sampling frequency as last time, but our system clock frequency is going to be a lot higher than in the previous example, because that was one of the issues, was that our sampling frequency was our system clock frequency in the past. In this waveform, I'm going to generate a 500 kilohertz sinusoid and then add 4 megahertz noise. Again, that 1.65 volt offset, that's to simulate the positive only ADC. Everything gets quantized and assigned to like a sample. And then this block here wasn't in last time, but what this does is automatically puts the file into the XSIM directory. I showed where to put that last time, but I used a little bit of file IO in this script to just do it automatically. I also created a file called impulse response output, because I'm going to show you how I'm measuring the impulse response using the Verilog Testbench. Then we can go back into MATLAB and verify if it's correct or not. Next, I'm going to generate the filter coefficients. I'm going to do a low pass elliptical filter with a cutoff of 1.5 megahertz. So this should eliminate our high frequency noise and then pass the 500 kilohertz component. Again, similar to what we did last time, just with different cutoff frequencies and parameters. I'm going to run this section, this above section, and show you what the waveform looks like that we're trying to filter. So you can see it's a bit noisy, it's not quite sinusoidal. And then I'm going to show you the frequency response of the filter, or here's the pole zero plot and the frequency response. You can see our filter, it is indeed stable, and this is our frequency response right here. Then, similar to what we did last time, this code is also going to have a 16-bit sign multiplier width. So again, I'm going to need 1 bit for the sign. So 2's complement. The first bit is either a 0 or 1, indicating positive or negative. The next bit is going to be for the ones place, indicating if it's a 0 or a 1. Then we have 14 bits for the fractional part. So that's going to be our scale factor. So I'm going to round, or first I'll multiply the coefficients and then round them so I get nice integer fixed point coefficients. And you can see that down here. I have my A coefficients and I have my B coefficients. And this A coefficient right here, that is just going to be 1, the A0. That's that 2 to the 14th scale value. Let's check the stability of these fixed point coefficients. And, whoops, my cursor's acting a little funny, but you can see that they are indeed inside the unit circle, so we're okay after we did that little conversion. I'm just going to show an example of what we expect to get from the filter. So we do expect a nice sinusoidal output right here. And then let's take a look at the expected impulse response of the filter, which will be right here. And then this part right here, I'm not going to run yet because I want to get the actual impulse response from my Vivado simulation, which hasn't been compiled yet. So we're going to go to the Verilog code. Here's the Verilog code. This is the module itself. I have a pretty detailed description. I think the coefficients are Q1.14. I'm not too familiar with the Q format, so please correct me if that's wrong. One important thing to note is the input and output data width and coefficient width are adjustable. However, these do have maximums. So for the Xilinx, I'm using the 7 series DSP48E1 tile. It's got a 25 by 18-bit multiplier, so you're not going to want to exceed that width in either of the parameters. So for example, you could have your max coefficient width 25 and your max in-out width to 18, and that would satisfy those parameters. It can't like, I'm not sure how the synthesizer would work if you were outside of those parameters. But I had mentioned last time one of the issues with the last code was the lack of parameters. So you can see here I have quite a few parameters that are easily changed. Let's go down here. Okay, so I have my parameters. I have the coefficient bit width, which is 16. I have my input and output data width, which is going to be the same. For me, on the AXI-Stream, it's going to be 16 bits wide. And then I have my scale factor. I'm not sure if scale factor is the right word, but it is what I multiplied the coefficients by to get those integer coefficients. Again, I did that in MATLAB. Here are my coefficients. I have my clock, my reset n, and then I have some of the AXI signals. If you don't know about AXI-Stream, I will link a video in the description below of how you can learn about it. I'm not going to go too in depth on it because, in my opinion, this isn't a great implementation of the AXI-Stream. However, it does work, so it's definitely open to a lot of improvement. I have the valid signal coming from the slave. I have an input which is on the master side of the module, and that's going to be for the upstream device ready. I also have the slave data, the slave side data, the master side data. So this is going to be your output data, and then the slave side is your input data. The slave I'm referring to is going to be the downstream device, and the master is the upstream device. I have an output valid signal, and then I have an output ready signal. And it might be a little bit confusing. Output S AXI-ST ready. So that refers to the slave, but it's going towards the slave. So it's coming out of the module on the slave side towards the slave. So it's the module ready signal to downstream slave. Again, this input, this is on the master side, but it's for the upstream device. It indicates whether the upstream device is ready or not to receive data from this Biquad. I have my filter coefficients, getting their values from the parameters above. I have an input register. I have a couple output registers for signals that we'll be manipulating, such as the master valid and the slave ready, as well as the master data out. Similar to the last code, I have my delay registers and my multiplication wires. I have my accumulate wire. And to cover the AXI signaling, I made a short little state machine. So the ready state is when the module itself is ready to accept data, and the busy state is when the filter is actually working and chugging out a filtered sample. I also have a control signal to enable the IIR filter. This is my state machine. The rule when you're using the AXI-Stream is you always want to logically, or not logically, but you always want to AND the slave ready and the slave valid. So the slave ready is going to the slave device, and the slave valid is coming from the downstream module. You want those two to be ANDed together, and I only want to enable the IIR filter. So I only want the busies when the filter is enabled. I only want to enable that when both of those signals are high. Otherwise, just stay in the current state. Then once we're in the busy state, we're going to say if the output signal is valid. So if it's valid, then we're going to head back to the ready. Otherwise, just wait for the output signal to be valid. Here's our output logic, just showing what happens within the different states. So in ready, we're not going to have an output valid. We are going to be ready to accept data, and we're not going to enable the filter. In the busy state, the valid's going to be high. The ready's not going to be ready. We're not ready for new data yet, but the IIR filter enable is high. So that IIR filter has been enabled. This covers the state update logic. This is the AXI-Stream handshake to the upstream module. So this waits to make sure that the upstream module is ready right here. And if it is, only then will we send the new data. It's important to note that this doesn't have any FIFOs in the design at all. I put a note somewhere here. Maybe I didn't, but there's no FIFOs in this design, so it's not going to be able to hold unread data. So if you don't read the data on time, the data is just going to go away and it will continue on as normal. I'll show you an example of that in the simulation. This should hopefully look familiar. This is very similar to what we were doing in the last module. I did add the reset, which resets all the delays to 0. Here's that arithmetic right shift. I got it wrong in the last video. It's a right shift, not a left shift. So I apologize for that. But again, with there's the arithmetic right shift to do the division by our scale factor. And then there's the update of all of the delay registers. Exactly the same as the last modules, our multiply wires, our accumulate wires, and then some output assignments. So pretty straightforward so far. If you have any questions, please leave them in the comment section and I can get back to you about it. Let's move over to the test bench. So here's my test bench. I have all of these to view the output signals or manipulate the input signals. Our clock is going to be a lot faster because we want to simulate a faster system clock with a lower sampling frequency. That's what we couldn't do with the last module. I have some coefficients for my module instantiation. Here I instantiate my unit under test. I have some variables for the test stimulus. Here's a new one. It's going to be the impulse max, and that's for the impulse response to create the maximum impulse for the width of for the data input width. These two status flags are to know, it's for me to know which mode I'm kind of in, because in this test bench, first we check the impulse response and then I apply the test stimulus wave that was generated in MATLAB. So it's just to know which one I'm doing at the time. I have 250 samples that were generated instead of 1,000 like the last video, but I do have that 2D register to hold the test waveform stimulus samples. I have a task right here, which generates an impulse and transmits it over the AXI-Stream to the module. So first I'm going to make sure that status flag goes high. I'm going to calculate the maximum impulse for the size of the in-out width, which for my module is 16. I'm going to wait for the reset to go high. Then I'm going to wait for the positive edge of the clock. Then only if, and again, this goes back to anding together the valid and the ready, only if the ready is high, then we're going to send out the impulse and we're going to say the valid. Then we're going to bring the valid back to 0. It's only going to be high for one clock cycle. We're going to wait for the next positive edge of the clock and bring the impulse back to 0. Again, an impulse is just going to be a single impulse. I'll show you on the simulation. Then for about 50 samples, or exactly 50 samples, we're going to keep the impulse at 0 or the input at 0 and just keep chugging out valid edges so it's just 0, 0, 0, 0. This is not a step response where it goes up and stays at a certain level. An impulse goes up for one sample, comes back down, and then stays at 0 for the rest of the time. To finish up the impulse task, I'm going to deassert that checking impulse response flag. Here's some file output generation. This is going to be useful for our MATLAB, and I will show you it at a later point in the video. But I'm just going to make this file for now, and on every positive edge of the valid signal, I'm going to write what the output data is to the file. And our output data, so we're inputting an impulse, so our output is going to be the impulse response, and I want to be able to measure that. So that's what this does, is it makes a file to measure the impulse response. This initial block right up here is random upstream device ready deassertion. So I just have some random amounts of time, and this is to show that when the upstream device is not ready, that the IIR filter is still going to work, but it's not going to chug out data, because you don't just want to be sending data out if the upstream device isn't ready. Again, there's no FIFO, so any unread data will be lost. This is my main stimulus initial block. Whoa, kind of got away from me there. I start by initializing all of these signals. I pull the reset back high, and we're going to check the impulse response. Then we're going to load the test stimulus from MATLAB from this file. And again, that needs to be in the XSim directory. The MATLAB script should take care of that. If it doesn't, please check the previous video on where to place that. Then we're just going to repeat for the number of samples. This block was in the last test bench for our 250 samples, and output those over the AXI-Stream slave data line. So, yeah. Okay, so I'm in Vivado. I've created a new project and I've added my sources. You can see I have the Testbench as my top module, and then the IIR DF1 Biquad AXI-S as my unit under test. I am going to run this for a short amount of time, and then I'm going to zoom in here a little bit more to right here. In this, I have the, let's see what my settings are right now. So I'm an analog, and I have my interpolation style set to linear. We could do hold, and it'll look a little different. So you can see the impulse right here. What I like to view it as is the linear style. So I'm going to switch it back to linear. But I did want to note that because it looks like the test stimulus is just increasing. It's not. That's just the interpolation from the simulator. But we can see zoom in a little bit more. We can see our impulse here. And then this is our output. So the MXEST data, that's our output data. And we can see our impulse response actually right there. This is our checking impulse response flag, so we can see it's high, so that's what we're doing right now. And at this point in the test bench, we should have created a file and have all of these samples of the impulse response in that file, which we can then read from MATLAB. I'm going to zoom over a little bit and maybe zoom out. Okay, so you can see the noisy signal, that's our input. And then you can see the nice, I'll go over this part in a second, but you can see the nice smooth sinusoid. So indeed, it did filter out that one frequency. This section right here is where the upstream device has said, oh, I'm not ready for data right now. So the filter it doesn't hold the data, but it just stops outputting the data. Again, this line here is because of the interpolation mode. It's not actually outputting this. It's just a line from one point to another point. So now that I have the simulation run, let's go back, and I have my little impulse response section over there, and then this section which just checks the wave output. I think the impulse response is a lot more useful I'm going to go back to my MATLAB, and then I have this last section right here. I'm going to get the impulse response out of the FPGA simulation. This is more file I/O stuff, but I am going to plot it down here, and I'm going to plot it with also the impulse response that we saw before, which is with the filter we generated in MATLAB. So I'm going to go ahead and run that. You can see here. So the blue is going to be our simulated FPGA filter response. So the impulse response that we got out of the FPGA simulation. And then this red is going to be what we see in MATLAB. So there is a small delay here, and that's because of the delay elements or the registers within the FPGA. But it does look pretty close. It's not exact. You can click on some points, but it is pretty dang close. So the next thing I did, and I'm not sure if this is the most efficient way to do this, but it's the way that I came up with. And if you know a little bit about signal processing theory, you can take the Fourier transform gives of the impulse response, the Fourier transform of the impulse response. Let me say that again. The Fourier transform of the impulse response gives information about the frequency response to the signal. So we can take the magnitude of the Fourier transform of the impulse response, and that's actually our frequency response. So that's what I did in this top section right here. Is I used MATLAB to take to do an FFT of our output from the file, from the Testbench file. I also tried to do this with phase. I think I messed up a little bit on this. It doesn't exactly match up, but you can see, and then I have generating our original frequency response that we did in this section at the beginning of the video. So let's see what that looks like. All right, and I did forget a title on this figure, but this one's going to be our one out of the FPGA, our fixed point Direct Form-1 Biquad, and then this frequency response and phase response is our prototyped one in MATLAB. So you can see they're okay. They're sort of close. We have in the stop band, it's a little bit different, but it does look pretty similar in that pass band. So let's just check a couple points here. So I have that point, and then because this isn't a lot of points in this FFT, it's not going to let me have the exact same resolution, but you can see it's pretty close. Again, the phase response is a little mixed up. I'm not sure what I did wrong there. If you see something, I'd love it if you let me know about it in the comments below. So thanks. That's this video, and then in the next one, I'm going to show you how you can string together multiple of these biquads and create a higher order filter.